Welcome to the Mechanics of Solid lecture series. In this next multi-part series, we will solve some simple examples demonstrating basic concepts of stress and strain. The lesson objectives, what I want you to be able to do after we finish the lesson, is to apply concepts of stress, strain, and Hooke's law to evaluate stresses and strains in engineering bodies. Some examples that we'll look at are subassemblies with tension members and rigid members, subassemblies with pin connections, and subassemblies with rubber blocks deforming in shear. Here's the first example, and I'd like to acknowledge that the graphic comes from the Mechanics of Materials book by Timothy Philpott, Wiley 3rd edition, and the example is very similar to a problem in that book. What we see here is we have a subassembly with a tension member, a bar attached to a beam carrying a distributed load, and connected at both ends with pins to rigid supports, pin A and pin C. The given information is that the distributed load W is 25 kilonewtons per meter, the length of the beam is 1.7 meters, the angle of the rigid bar to the beam is 35 degrees, the area of member 1, the bar, is 3,000 millimeters squared, and the diameter of each of the pins is 30 millimeters. We might also recognize that if we look at the pin connections in the graphics shown up here, pin A is acting in single shear because the force is transferred through the pin only at one location between these two members. However, pin C is acting in double shear because the force is transferred through the pin at two locations between the members in two different locations. Okay, so what we're asked to do is evaluate the tensile stress in bar 1 and the shear stress in pins A and C, and for now we specify that we want these stresses in units of megapascals. So to summarize what we're asked to find, we're asked to find tensile stress in bar 1, which I'm going to call sigma 1, the shear stress in bar A I'm going to call tau A, and the shear stress in bar C I'm going to call tau C, and all of these in megapascals. A few words about units. Anytime we're dealing with stresses in standard units, we like to use and specify those in megapascals. Gives us nice numbers. A megapascal, 1 megapascal, is equal to 10 to the 6th Newton per meter squared. However, this is not very convenient at all, but it is also equivalent to 1 Newton per millimeter squared. So I like to think of a megapascal as a Newton per millimeter squared. Therefore, if I'm calculating stresses, I want to convert the forces to newtons, and I want to convert length, or area if you will, to millimeters or millimeters squared. We usually don't have to worry about the areas, but forces are often specified in kilonewtons, and we'll use the conversion factor. 1 kilonewton equals 10 to the 3rd newtons. Okay, so without further ado, let's get started on this problem. What free body diagram should we evaluate? Let's consider what we have to find. We have to find the force in member 1. We have to find the force across the pin, which is going to be equal to the force in member 1. We have to find the force across pin C, which is going to be equal to the resultant reaction at C. So I want to find force in member 1, the reaction at C. I'm going to draw a free body diagram of the beam right here, and that will give me all the information that I need to know. Here's the picture of the beam. Okay, for now, for this problem, I will represent the distributed load as a resultant, WL equal to 25 times 1.7, and the resultant units are kilonewtons. I will draw my unknown force in member 1, which I'm going to label F1, and I will draw the reaction in at C, which has components C sub x and C sub y. Okay, so there's my free body diagram and everything I need to consider. Not showing the lengths, but we can easily infer them from above. I could start anywhere. I think I will start by summing moments about point C, which will allow me to directly solve for the force in member 1. Sum of the moments about C, taking moments in the counterclockwise direction to be positive. F1 produces a negative moment about C. Only the component in the vertical direction will contribute to the moment about C. The component acting in the horizontal direction passes through C and so does not contribute. So we have F1 times its vertical component, or decomposing to the vertical component, which is sine of that angle, 35 degrees, okay, times the moment arm, which is simply the length of the beam, 1.7 meters. Okay, and this is acting in the negative direction as we said before. The force WL also contributes to a moment about C in the positive direction. So we have 25 times 1.7, that's the force in kilonewtons. Multiply that by the distance, which is half the length of the beam, 1.7 meters over 2. That's my distance. Okay, those are all the terms that contribute to a moment about C. Set that equal to 0. I can solve for F1, reverse the sign. F1 equals 25 times 1.7 squared over 2. This term has units of kilonewton meters. It's going to be divided by this term right here. Sine of 35 times 1.7 meters. My meters cancel out, and the result is, doing the calculation, we would get 37.05 kilonewtons. That's the force in member F1. Positive, meaning that it's in tension.